odd thing to say is the first thing after we start recording, but I guess this also serves as the you've been notified on recording that you are on recording. Apparently, they have decided that a three-person class counts as option two from our discussion last time, which means essentially that this class is not part of my formal teaching load, but it is an overload somehow that I'm being paid as if I'm an adjunct to teach.
Cool.
So apparently that's how that is working out. I guess I count that as a win. I'm still going to see about getting folks to audit and all that. So let's jump into today. We're starting in on lecture set 6. Oh shoot, I don't have my writing thing open though. Sorry. Let me open that and then we'll jump into today. I have all the other stuff that I thought I needed open. Put this over here. Yeah, this will be fine. Let's go full screen and let's make sure that I've got the right screen shared. It'd be this one. Ignore the title. We're not talking about Bell predictions. Um, all right, and this is not quantum one, obviously. This is quantum two. I've got a couple little rando logistics, but they're not going to affect today. Um, so in our kind of the end of last class, we had talked about bound states, specifically um, states in square potential wells. Um, maybe depending upon when you took it or who you took it from. Nathan, I don't know if you got into potential wells at all in your quantum one class or not, but sometimes you have a little bit of perturbation theory in there for like the well that is. Come on. Sorry. Hang on a sec. I've got everything kind of backwards. My tablet is set for the wrong screen. So I went to write and then it was like, you can't write here. You can't fight in here. This is the war room. You can't write in here. This is the notes card. All right. Let's try that again. All right. So in the last class we had, or in the last course, we had like the square potential wells. And so, we assumed a potential more or less of this form, whether finite or not. And then depending upon how far you read, got, etc., you might have had a potential well that did this, where there's like a step somewhere in it. Oh my gosh, this is the downside. Hello? Here we are. Okay, so you may have had something like this to face, that kind of thing, where your energy levels would be something like this, lower than your potential essentially. Okay. So now we want to look at unbound states. So this is bound. This is unbound. Okay. And um, we might consider, for example, states actually like this that are unbound, but with a well present. We can also consider conditions like this. So again, the yellow represents the potential energy. This right here is also an unbound state. This right here would be maybe a partially bound state that has some possibility of tunneling over here. Okay. And so we want to look at these kinds of states and what they're going to do. Before we get anywhere else, a reminder, and I kind of stated this at the end of the last one, but it's always nice to revisit. We're effectively solving our energy eigenvalue equation where this right here, the Hamiltonian operator operating on a state that is an eigenvalue of the operator, gives us the energy of that state, the eigenvalue, times the state, okay? Where the Hamiltonian operator continues to be written in position representation for now, but where in general, it's the momentum operator squared divided by, your mass, and then a position dependent potential energy operator. Okay, and we will work in wave function language as before, and we'll do it in position representation as before. So this basically, in that representation, looks like Hamiltonian operating on some phi of x gives me energy times some phi of x. And this Hamiltonian operator written out, I'm going to switch to a slightly finer nub here. This operator written out in position representation becomes h bar squared over 2m, d squared by dx squared. Remember that this is the momentum operator squared, so we operate twice, plus v of x. Remember that in position representation, the x operator just is x, the position, times phi of x is equal to E times phi of x. Okay, so this is basically what we're doing. And what we want to start with is the very, very simplest of all possible unbound states. What is the very, very simplest of all possible unbound states? Well, it's the one in which this term right here goes to zero. Can you see my mouse, by the way, when I do this? I'm just going to underline it because I don't know if the recording also picks it up or not. So this state will go to zero. So simplest case, oh, hey, I can make the nib a little smaller. Simple case is this. So this is a free particle on which there are no potentials acting. Okay. Um, so what is the energy eigenstate for this free particle? Okay, well, we can rearrange this equation to become d squared by dx squared phi sub n of x. And basically, I'm just multiplying both sides by this term because this term has gone away. The h bar squared over 2m is multiplying both sides because the v of x has gone away. Okay, so that's going to look like 2 times m times e, or e sub n, over h bar squared, negative, and that is equal to phi of x. Okay, so essentially we're looking at this, and you can combine all of this into k as we did um, in the well case. So if we represent all of this by k, then we have the same equation that we had in the infinite square well. And so what you end up with is d squared by dx squared phi sub n of x is negative k squared phi sub n, left off the subscript there, phi sub n of x. And so this is actually the same equation that we had in the infinite well. Um, and and k then was our wave vector. Um, this obviously is a very simple differential equation. What is the solution to this equation? Well, you can either do cosines or cosine with phase, or cosine and sine, or exponentials. And we're going to go ahead and do the exponential form of the solution. In the infinite square well, we went ahead and did the sine and cosine. Okay, here we'll go ahead and do the other form. So what function solves this equation? In other words, the answer is that this has to be of the form a e to the I times kx plus b e to the negative I kx. And if you'd like, you could put a positive sign here for completion. Okay, so this solves the differential equation that we have at hand. Does it solve it though? Well, yes, it solves it as a general thing. It has not solved it in a complete sense, right? Why not? Because we don't actually know what the values of the energy are here, of the possible energy values. And so therefore we don't know the value of k. We also don't know the values of the two coefficients, a and b, the amplitudes. Might as well bring tea to class since we're doing it this way. You guys should feel free to bring coffee or tea when you do this. Um, it's like a good
A quick
virtual
question,
seminar.
Dr. Sanders, if I
Yeah,
may.
sure. Go ahead, Nathan.
So this you have got k defined here, and then we've got k squared. So would k be the square root of 2m times e sub n over h bar without the squared?
Yes,
I just
yes. I
want
left off.
to. Okay.
I meant to define this term here as k squared. Thank you. Thank you. That's a good catch. This was meant to be k squared, or if you prefer, you're correct. You could also say k is just square root 2 m e over h bar squared. By the way, I've said e over h bar squared, and I've said e sub n here. I'm doing that kind of as a throwback to the fact that we had e sub n values. When you are unbound, you may actually be more like a continuum of energies. And so I think it's very fair to argue in that case that maybe this should not be an E sub n, but just an E. And in fact, in the original notes that I wrote out, I had it as an E. Um, with that said, part of why I left the sub n is just to be consistent with my previous notation of the phi's, as phi sub n corresponds to E sub n. But they may be a continuum, so n may not in this case mean n equals 1 or 2 or whatever. So with that little caveat aside, how are we going to get A, B, and E? How do we determine those things? Well, it's kind of rough because we can't. We can't actually determine all of those things. We have 3 unknowns. We actually only have one equation or one condition that we can evoke. What is that condition? What can we invoke for this case? And again, if it helps, I'll draw for you. Here's the potential energy. We're unbound, so we have an energy that is somehow greater than that. And beyond that, I can't say anything. It may be there, it may be here, maybe here. Um, Sorry, something just popped up on my side window. Uh, no, did you hear that?
No.
Okay, maybe it's just me. Is the warning the warning you've made an error thing? But we're good. What condition do we have to work with here? And one way that I can ask this question a little differently for you guys is by way of contrast. Suppose that we wanted a bound state. So in a bound state, I'm going to draw the bound state in red, or the potential for the bound state in red. Suppose I had this instead of the yellow that I have here. Okay. So actually have the yellow. What if I have the red?
Then you'd
What
have
would be,
dimensions to your well. So we have to
yeah, I'd
define
have
our,
some stuff for the well, right? Like
yeah.
I'd have like a length scale for the well. Um, but
Would
it
we
gives me
define our
like,
boundaries at infinity then?
exactly, exactly. We would have two boundary conditions for this well as a bound state.
Right.
And so I'd have two locations where I could apply boundary conditions. And the result of that, I'd also then have like an equation form for here and here that would be real exponential decays. So it'd be like e to the uh, plus qx over here, and e to the minus qx over here, where q is the difference between your potential energy and your actual state energy. And now these things have to be continuous and possibly smooth across the boundary. So that gives me minimum three conditions, right?
Right.
I have continuity across the left boundary, I have continuity across the right boundary, and what's the third condition?
Give them to me again, Dr. Sanders, if you don't mind.
I have
What-
continuity across the left, I have continuity across right.
Then there's your well depth.
No, that's included in K and in Q.
Okay.
We've already in some sense tried to include that information. There's a third
Normalization.
thing. There you go. James has it. I was about to say, by the way, I only see when I'm in this mode one person, which is Nathan. So I was about to check whether you guys were there or not. Not because I don't, not because I care if you are quiet or not, but just if I've dropped you, I don't want you to be like, this guy, he dropped us and then he ignored us. But
Yeah.
yeah, James has the right answer. You guys are there.
Mine
Cool.
mine would be on, but when I logged in, it said I don't have one connected, which is odd because there's
Okay.
one attached to my
Yeah,
laptop.
now it shows your icon.
Yeah.
Showing your icon now. It wasn't showing when I'm in presenter mode. It only shows either one person or icon at a time.
Oh.
So feel free to occasionally just chime in, but say like, you know, whatever. Dang it. I
What was the
just
answer though? You guys stepped on each other a little
so
bit when
yeah, sorry about that. So James had the answer. The third condition. So first condition was left boundary. First condition left boundary. Second condition right boundary. Third condition normalization.
okay.
Okay. So those are the three conditions that we had to work with this well. So now we take the well away. What does that change? Well, I no longer have a left boundary, so that one's out. I no longer have a right boundary, so that one's out. I still have normalization.
Don't you still have a boundary at negative infinity and positive infinity?
No, that's not a boundary.
Okay.
There's you don't have a particular point in space where you say this is minus infinity.
Sure.
The I think what you're thinking of actually probably will fall more under normalization. You have a condition that it cannot blow up when
Right.
you go to plus and minus infinity, but
Exactly.
that's not a boundary. That's
Okay.
normalization. That's making sure the thing is properly normalized. Um, and yeah, so at this point, 3 unknowns, A, B, and E. K and E are the same as each other. One equation or condition, that's normalization. Okay, so first of all, why is normalization still valid? Well, because what is it that normalization, like why does it have to be normalized? What is it that this thing tells us?
You can't have a probability of more than one.
Right. This thing fundamentally is telling us about probability. It's a probability distribution. If I integrate this over all of space, then I'm finding, well, this times its complex conjugate over all of space. If I do that, then I'm finding what's the probability of the particle existing somewhere in space. The answer is 1. It has a 100%. If the particle exists, then it exists. It's a 100% probability. It can't be a 500% probability. Okay, so normalization is still there. Now, what is an implication of this fact that we've got 3 unknowns in one equation? Well, one of them is the thing that I was hinting at earlier. And you'll notice that I've now dropped the sub in here. One of the consequences of this being true is that E is no longer a discrete state. So the fact that E is a continuum is actually a consequence of the fact that we have no way to sort of bound it, if you will. Okay. Does that mean that E is necessarily infinity? No. It just means that it has some value between, let's say, 0 and infinite, and that it's been bounded by those 2 points. Um, Let me think if I want to say anything else about that. Not really. There's no boundary conditions, so with a free particle, energy is continuous rather than quantized, is sort of the take-home point. All right. Again, we're still trying to do the simplest case. What do we usually do once we've found the state or states? In the past, what we would have said is, okay, well, we found our quantized energy states and our energy values and our state values. Now what we found is, well, there is not a quantization of the energies. Okay. We just have some state that satisfies our equation. Does the state evolve in time?
No.
Shouldn't, right? If it's an eigenstate, eigenstates are what we call fixed states. We talked about this in quantum one. A fixed state is a state that doesn't evolve. So our state should not evolve in time. So let's kind of do a gut check of that. What does Schrodinger time evolution say we should do? Well, basically, we apply the same recipe as we've had before. Okay, what's the recipe say? It says if I've found an eigenstate, and I'm going to go ahead and write that eigenstate like this. I know it's a bit of a change in notation, but mostly I'm doing this because we've gone from these in the well to this out of the well. And we want to go to that state later in time. What should that look like? Well, basically, it should look like your original state times a phase factor. And that phase
Right.
factor always looks the same in this Schrodinger evolution. It's negative E to the I times the energy times the time divided by h bar. Okay. So that means that our state in this case, or simple unbound, I'm just going to call it the simplest unbound. You have psi e of x is a e to the I kx plus b e to the negative I kx. So what is that going to look like in terms of the time evolution?
So you're going to put a parentheses around your wave equation and multiply it by e to the negative IET over h bar.
Right. Or alternatively, we can do what we've been doing and say like let E equal h bar omega, just to change this into an omega t as we've been doing. And if that is the case, then yeah, you go a e to the I kx plus b e to the negative I kx. You just stick a parenthesis around the whole thing. They all have the same energy associated with them. This is a t. And you just multiply it all by that. You can distribute it. So, you might write this as, and I seem to have lost a
Right.
subscript somewhere along the way. A e to the, let's say just I times kx minus omega t, and b e to the negative I kx minus, plus omega t. Is that writing clear for you guys, or am I getting a little too small there?
No, it's great.
Okay. Should be fine. You all should have like decent enough resolution to see it, but if it ever does get too rough, don't hesitate to let me know. Okay. Why would we want to do it like this? Well, because then we could maybe pull some terms, like for example, a K term we could pull out. Before I pull the K term out, just looking at this, just looking at the form of what's in the parenthesis, does that look like anything to any of you guys? And maybe for posterity, any of you gals, if there are some women watching this in the future, I'm sure there will be. So let me, whoops, sorry. Every time I go to scroll, it decides, or every time I go to change something, it scrolls. Let's just look at this term right here, and as well as this term right here.
I mean, it's the wave equation.
Yeah, it looks suspiciously like what you would get in like a traveling mechanical wave, right?
Right.
Like mechanical wave, so sort of like mechanical wave. You'd have like, let's say it's a wave on a string. You'd have like y of x comma t is equal to some amplitude. We could call it y max. And then you could have a cosine or a sine. Let's do a sine.
Yeah.
Like so. where this right here is sort of a phase offset term, and whether you've chosen minus or plus determines on whether you want your wave to be moving from left to right or from right to left. Okay, so just looking at this, you should be keying in on this looks like something I've seen before. This looks like a wave, and I know how waves behave. And, again, like that it is a wave. The whole damn point is that this is a wave. So that's should be comforting that it looks like this, right? Because we could have written it this way. So let's go ahead and take these terms and maybe pull a K out of everything so that we have this E. So we have A e to the I K times X minus omega over K T, and B e to the minus I K X plus omega over K T. And then we remind ourselves, what is it that omega over, sorry if you're still writing that down. What is it that omega over K is actually? Well, K we defined up here as in terms of energy, but I also kind of gave it away earlier because I said this is like your wave vector or your wave number. Remember that wave vector is 2 pi over lambda. And so if we come down here and say, okay, recall omega is 2 pi over period and K is 2 pi over lambda, or a wave, then this term omega over K becomes 2 pi over T divided by 2 pi over lambda, which is lambda over T. And what's lambda over T give us? Again, think back to mechanical waves.
Amplitude?
No, not amplitude. James, you want to take a stab? You want to take a guess?
Is that like velocity?
It is. It's the speed at which the wave propagates. So this is equals V. The wave speed is lambda over T, or sometimes we also write V as lambda F, or lambda nu if you'd like. Okay, so we've got a wave speed. Specifically, this is phase speed. Now, if we only have one frequency present, then phase speed and group speed are going to be the same. If we have a wave packet where there are many different frequencies present, then you have phase speed, which is this, and you have group speed, which is the actual speed at which the wave packet itself travels. Okay. So this is good. We're getting stuff that's looking very wave-like. That's what we want. All right, so now we have something that's in the form of a wave traveling either in the positive or the negative direction, depending upon whether you have this term. This is travel left to right, and this right here is travels right to left. Okay. So let's say that we want to just use our wave vector eigenstates again. Okay. So wave vector eigenstates means that we shift from basically the notation is a shift from this to this. Okay, and that right there becomes a e to the I kx, where k is either positive or negative. Okay. This we're going to leave for a moment. We'll come back to it. Because now, whoops. Now what we want to do is shift over and say, what about momentum? And we focused a lot on position. What about momentum? Okay, so if I have the momentum operator operating on this guy, okay, what do I expect that to look like? Notice that I'm still in position representation. Okay, so that means that my momentum operator is actually given by negative I h bar d by dx. Okay, and so that means that what we have is something like this: negative I h bar d by dx of, let's say, a e to the I kx. All right, so I take that derivative. Straightforward. Remember that a is just some constant, so we're only really looking at this term for the derivative. And so that means that this right here becomes negative I h bar, and now I have to take this stuff, so I have times I k times a e to the I kx. And so maybe I should multiply stuff. So I have I times I is -1 times negative is just positive. And so I'm left with h bar a e to the I kx. Okay. Oh, whoops, left off a k on this side though. Okay, so what does that mean? It means that the momentum operator operating on this guy gives me h bar and k times a e to the I kx. So this works. I have the same state multiplied by a constant. In other words, I now end up with h bar k psi k of x. So this state is also an eigenstate of the momentum operator. Okay. And then the other thing is that I look at this and see that P is h bar k. What are h bar and k again? Well, k we've written up here. H bar, you'll recall, is the reduced Planck's constant. So that's just h divided by 2 pi. Okay, so this right here, basically, we could call this P times psi sub k of x. P now is the eigenvalue that goes with the P operator. So my eigenvalue, lowercase p, is equal to h bar k. But that in turn is 2 pi divided by lambda times h over 2 pi. So if I cancel off the 2 pi's, I'm left with h over lambda. Now, where have we seen that before? E is h over lambda. That's the same thing as saying p times lambda is h. Where have we seen that before? We haven't in quantum mechanics, but you've probably seen it in your modern physics class. If you go
Wave
back
nature of
that far.
matter.
What's that? Say again.
Right. The weather's getting pretty bad over here. I
Oh,
might be coming in and out, but it's the wave nature of matter. I can't remember the physicists that came up with that.
you are correct. It's basically your wave associated with matter. the physicist's name was de Broglie.
That's right.
So this
de
is the
Broglie
de
wave equation.
Broglie
Yep.
relation, and this lambda would be the de Broglie wavelength.
Yep.
So if you'd like, you could also rewrite this equation yet again as lambda, and maybe you rewrite it as lambda de Broglie is h over p. These are all, of course, the same equations, so it's maybe a little excessive to have them all, but there you have it. Okay. So wavelength and particle motion are therefore related. And you're right, it gives us a key detail with that whole particle wave duality that we get. In pre-quantum mechanics, we had that duality as well. It would have been focusing on it in the form of optics, right? And even then, I think you'd have to say, yeah, is that really pre-quantum mechanics? Because until Einstein gave a solution to the photoelectric effect, until that happened, we just thought light was a wave. Everything light did was explainable in terms of a wave. But light was sort of like the first thing that was, okay, well, this seems to be a wave and also a particle. Then along comes de Broglie and others, and gosh, all these things that we thought were particles also have a wave nature. And this is baked into quantum mechanics. We just did all this above the board. I didn't, there was no step in here that was like, gee, that's really dodgy, right? Each of these steps followed from the others. We solved an energy eigenvalue equation for an unbound free particle, and checked our definitions and everything, but ended up very logically with de Broglie wavelength. Okay. Another thing worth noting in all of this, x is a variable. Okay, its position. P is a particular momentum eigenvalue. So these momentum eigenstates that have particular values are also energy eigenstates. They're energy eigenstates that have energy E is P squared over 2m. Which should make sense because that's how we defined our Hamiltonian, right? Well, we had a plus v of x term, but remember that we're still looking at a totally free, unbound particle. V of x is 0. So this is p squared over 2m. There's no v of x term left. Okay, that means that both momentum and energy share common eigenstates. What does that mean is going to happen? Momentum and energy share eigenstates. So what is that? What can we conclude therefore? What can we say about their operators?
They'll be equivalent.
Not quite equivalent. They're not quite equivalent. E has as its operator p squared over 2m. P has its operator p. So they're not the same operator. Nice try. Let's try
Had
again.
to break the silence.
What do you think, Chip? You still there, man?
Yeah, I'm here.
Good.
But I do not know the answer.
You don't remember?
Is it
Right.
about
But
the
the-
eigenstates? Or-
Yeah, we said that they share common eigenstates. And so
Mhm.
we asked, what does this mean about the operators?
Is it like they commute or
That's right. That's the word we're
Yeah.
looking for. When you share common eigenstates,
Mm-hmm.
your operators commute. What does it mean if their operators commute? Now going back to quantum mechanics, what happens if you have two things whose operators commute? What can we say about those two variables? Let's change it from the word variable to the thing that we usually talk about in quantum mechanics. Well, one thing we talk about. One key term that we talked about, especially in the early chapters, starts with an O. It's not operators. Starts with an O and ends with a observables.
Observables.
Yeah. What do we know about the observables if the operators commute? Anyone remember?
I don't
All
mind
right.
making wild guesses. Is it a two-state system?
No, it's not a two-state system. So if the operators that go with the observables commute, it means that the two are compatible. If they're compatible, that means that you get to know their values simultaneously. So you can simultaneously know the value for energy and momentum for this system.
Yeah.
If they did not commute, that would mean they are incompatible and you cannot know that. So again, reviewing quantum 1, S sub x and S sub y. Did these two commute? Answer, no. No, they didn't. We had a commutation relation. You had your IH bar S sub Z. So they don't commute. They're not compatible. And that meant that we could not simultaneously measure both spin X and spin Y. In fact, we could not simultaneously measure X, Y, and or Z. We could only know one of the three. Now, what was something that did commute with these?
S squared.
Right. The S squared operator commuted with actually every one of these. Okay. So that meant that we could know the value simultaneously within our system of both S squared and SZ. Here you could not know the two. It's getting real bad. Simultaneously. Okay, so these commute, that means you can simultaneously know those two. All right, and kind of getting a little over. I have one last little point to make. I guess we'll go slightly over and then that'll be sort of our stopping point for today. Do I want to do this? So we're going to have to talk about degeneracy pretty soon here. Let's hold off until next time. Let's do degeneracy next time. All right. So we'll stop here for today. I'm gonna put my little board out of the way. Are there any last questions before we, shut down?
Would it be possible for you to share those lecture notes from that PowerPoint file?
I guess I could. Like as I was writing these, it occurred to me that, yeah, I really could just save it. Bear in mind, one thing to bear in mind about these notes versus like having watched this. Remember that I was modifying them continuously as we went through, including in some cases erasing stuff and writing something new.
Yeah.
So I'll share them, but just bear in mind that it's not quite the same as having written your own notes and made. But I'll just save them as like day 1, day 2, day 3, etc.
Cool. Awesome.
Now everybody watching this on YouTube is going to be like, "Can I get those from YouTube?" But by then I will have probably deleted them. I have a finite amount of space on the hard drive, but I'll upload them to the course shell.
Awesome. Thank you.
All right. I guess I'll maybe before I stop recording and quit and all that, one logistics note. I think I said this in the announcement. I set up this virtual meeting as a recurring meeting. So that link that you all have should work for this every time that you want to access it. And it's just set to recur Monday, Wednesday, Friday at 11. And, you know, it is still going to say there's a meeting like on, this Monday is Martin Luther King Day. We don't have a class meeting, and there won't be anything here, but it'll still pop up as if there's a meeting. That's just me and Teams and not wanting to screw around with
Right.
the little stuff. So our next class should be Wednesday. And again, I've got jury duty on Tuesday to find out whether I have more jury duty or not. So hopefully I see you all at this time or at 11 o'clock, same start time on Wednesday. And if we do attempt something out of the classroom, that is also fine. I will just set it up, hopefully so that this streams from there. It doesn't look like our classroom has the streaming set up as the only thing. So I'm reticent to do that unless people really, really want to have a in the class day. So I'm going to go ahead and quit recording there.